Okay. Okay. The length of a vector. What is the length of a vector? So suppose there's a vector v. How do you define the length of a vector? Right. So what's the magnitude? Okay. But in terms of things that we know, right? That's absolutely right. So Mustafa, right, and Caleb. So both of you are completely correct. But I'm looking for something that we have studied in class. Tell me in terms of things we have studied in class. Pardon? Distance from the origin, that's very good. And let's write all of this because all of these are correct. I'm just insisting on some weird this one, but I have reasons for that. You're completely correct in all your answers so far. I'm giving you a hard time because because there's something specific we want to focus on. Okay, so you're completely right. If v is let's say v is a vector that is, let's say, x1 x2, or it could have more than two components, it doesn't matter. The length of v, which we'll write like this, we'll write the length of v like this. Okay, so this double bar signs, this is a general notation for what we call as norms. Okay, there are many different notions of length, but the length we will be concerned in this class is the length that you are familiar with. It's called the Euclidean length, or the geometric length. Okay, and this is the square root of x1 squared plus x2 squared. Okay, I mean, for a computational perspective, this is all fine. Okay, we are not, like I said, the purpose of this is not to learn to be computers. Computers can do better than us anyway. Okay, when it comes to computing, okay, it's to understand what is happening. The length is actually the so rather the length squared is x1 squared plus x2 squared. Okay, the length squared is the vector dotted with itself. Okay, that's the part I'm looking for. Okay, the square of the length of a vector is the vector dotted with itself, right? So this is the more fundamental. This is the more fundamental thing. This is a computational thing, right? So this is computational. Rarely have to worry about it. This is fundamental. Okay. What happened over there? I don't know. Like, I mean, these screens, they do very funny things now and then. But okay. So, but do you see, like, the length of a vector square? It's consistent with what you know. Okay. But we will see it as the vector dotted with itself. And remember, with dot products, one of the important properties that we wanted with a dot product was that the dot product was positive definite, or any vector v dotted with itself, okay, is greater than or equal to 0. And in particular, it is equal to 0 if and only if v is 0. Okay, so that means that if you define the notion of length in this fashion, right, all vectors have, all non-zero vectors have length strictly greater than 0. Every vector has length greater than 0. Okay, every non-zero vector has length greater than 0. The 0 vector has length 0. Okay, so is this clear? Okay, so this is the notion of the length, and like I said, once again, this is the more important part. Right? Completely consistent with what you know, you're just seeing it from a different perspective. Okay, now there is more to dot products. When you have dot products and lengths like this, dot products also give rise to the geometry that we are familiar with. But then, like, so here we are looking at vectors and we can do all this geometry. We visualize all this geometry. It all makes intuitive sense to us. Okay, but you could do exactly the same thing in spaces of functions. Okay, how many of you have taken 315? Yeah, signals and systems. Right. So 315 is, you're doing actually exactly the same things in 315, but with functions rather than vectors. Okay, you're decomposing. So towards the end of the class, we'll see something called eigenvalues, eigenfunctions, and they don't exist just for matrices, they exist for all linear operators, in particular for the differentiation operator too. And the eigenvalues and eigenfunctions for the differentiation operator are sines and cosines or complex exponentials. Okay, and that's why you're expanding everything in terms of complex exponentials. Okay, so right, so this is about, so keep in mind that even though we are talking about vectors right now, it's like a special case of a much bigger story. Okay, and you are actually learning about that bigger story without knowing that you are, right, as of now. Okay, good. So now we'll come back to matrices, and one of the things with the matrix multiplication that we have done is like, when I gave you two matrices, like some of you got the multiplication right, some of you got it wrong. That's not the point. Okay, but the thing is, like, the most elementary way to describe a matrix, it's a rectangular arrangement of numbers, right? So when you see a matrix, okay, one way to think about it is it's just a rectangular array of numbers. Sometimes makes sense, like if I have so a lot of data that we collect is naturally in this form. If I, for example, if I take the quiz scores of all students in the class, okay, I could construct a matrix of quiz scores. Each column corresponds to a particular quiz and each row corresponds to a student. Okay, so and this is the common way we arrange data, and it's not just quiz scores. When you're looking at protein data, okay, or when you're looking at genetic expression data, they do pretty much like that. Every row will be a gene, every row will be some kind of, so depending on exactly what you want, every row will be an example and every column will be a feature. Okay, if you're looking for many different people and you're looking for their gene expression, okay, the examples are the patients. So every row corresponds to one particular patient. Every column are the clinical features or the other features that you collect. Okay, like results of blood tests or results of gene expression values, anything you want. Okay, so all data is collected in this fashion, and usually the example we will use is columns are features. Okay, and every row is an example. Okay, so that's the conventional way we arrange data in across fields. Okay, so you'll also see the word attribute used instead of features. No difference. So examples are sometimes called instances. Just they're all the same thing. Okay. So the most elementary way is to see it as a rectangular array of numbers. This is fine for the data collection phase, okay? But we want to do something more with it, right? And in order to understand like how data interacts with this one, in order to extract information out of it, we need to see it in more and more powerful ways, okay? Right now we know about vectors, okay? So we'll make the next leap. Don't see this matrix as just a grid of numbers. Start seeing the columns and rows. Okay, every column is a vector. Every row is a row vector, right? And with vectors, we know a few things. We know how to add them. We know how to scale them. We know how to do linear combinations. Okay, and for the rest of the class, in fact, all we will do is to keep track of linear combinations. Right? And when we put these vectors in matrices and multiply them around and so on, essentially what we are doing is track the linear combinations of all these vectors. columns or the rows. Okay. Now, for matrices, so one thing is like any rectangular arrangement of numbers is a matrix. In particular, the vectors that we have seen, both column vectors and row vectors, they are special matrices. They're just matrices that happen to have only one column or only one row. Okay. The matrices have a size or a shape. Right? Python likes to use the word shape, so and in math typically use a size. They both mean the same thing, and we will use both of them in class so there's no confusion. So if a matrix, let's say there's a matrix A, and its shape is m comma n in Python, or m, we write it as m times n. Okay, this means it has m rows and n columns. Right. So, but m rows and n columns. Okay, the first number is the number of rows, the second number is the number of columns. Okay, so yeah, no, m is not the number of rows. The first number of the matrix shape is the number of rows. Okay, and here it happens to be n. Okay, you're right, in this case m is the number of rows, but n is not always going to be used as the number of rows. Okay, number of rows here. Right. So when we write the shape of A to be a number times another number, the first number is the number of rows, the second number is the number of columns. Okay. So tell me, if this is a matrix, okay, let's say this matrix A has m rows and n columns. Okay, every column of this matrix, pick any one column of the matrix. How many coordinates does a column have? Pardon? The number of rows. Okay, every column, the number of coordinates in every column is the number of rows. Okay, so for example, like suppose I write 1 minus 2 0 1. What's the size of this matrix or shape of this matrix? Not 2 by 2. Not 2. Yeah, it's 2 by 3. First is the number of rows. How many rows? 2 rows. Okay, the first number is always the number of rows. Okay. No, so this, when you go left to right, it is a row, but how many rows? You have 1 row and 2 rows. Okay, so how many rows? Yeah. Right. So whatever works for you, okay, you can remember it in any way that works for you, but you cannot have your own approach because you're going to communicate with others. Everyone in the world except the 30 of us uses this convention, right? So it's difficult to change the minds of everyone else. Okay, so yeah. So the number of rows is all in the size of the matrix. The number of rows is the first number. Okay, and the number of columns is the second number. Same thing with Python. Okay, Python also uses exactly this notation. They won't call it 2 times 3. They'll call it, Python will return the shape of this as 2 comma 3. Okay, but same story. Okay, now so this is, so if you look at any column, okay, any one column, the third column is 3 2. Okay, it's a vector with 2 coordinates. Any one row is a vector with 3 coordinates. Okay, good. Okay, yeah. Okay, so this is what a matrix is. Okay, we look at one specific kind of matrix multiplication, right? So Suppose, how many columns are there? 3 columns. Okay, and let us say I want to take a linear combination of these 3 columns. Okay, I want to multiply the first column with alpha 1, a number alpha 1, the second column with alpha 2, and the third column with alpha 3. Okay, so I want this linear combination. Okay, I want this particular linear combination. I write this linear combination as the notation for this is this matrix multiplication operation. Okay, when I look at this matrix multiplication operation, what I mean by this is that linear combination. Okay, that's all I mean by, that's all matrix multiplications do. They keep track of linear combinations. Okay, sometimes you may want to keep track of more than one linear combination at a time. Okay, let's say there is this linear combination. Let's say there's one other linear combination. Okay, so let's say there's beta 1. I'll write it in a different color. 1 minus 2 plus beta 2, 0, 1 plus okay, this could be another linear combination. Okay, I don't want to write out 2 equations like this. It's a lot of work. If I want to keep track of both of them, this is what happens. Okay, if I want to keep track of both of them simultaneously, I write this matrix multiplication operation. Okay, so when I'm multiplying this first matrix by the second matrix, what I'm doing is this. The first column of the product will be this linear combination. The second column of the product will be this linear combination. Okay, so that is all that is happening in matrix multiplication. Oh, okay. It's equivalent, but the dot product one is not conceptually that useful. It is useful. I mean, I shouldn't say it is not useful, but for now, the dot product one is not as useful as this way of looking at it. They're both completely equivalent ways of looking at it. They'll give you the same answer. Okay, the row multiplication that you learned in high school, when you figure it out, okay, you'll notice there's the same answer as this. It's not a different thing. Okay? But no one told you why you did that. Okay, so essentially, what matrix multiplication does is to just keep track of linear combinations. Okay, so now when you do this matrix multiplication, how many columns are there in the first matrix? 3. Okay, so how many coefficients do you need to make a linear combination of 3 vectors? Yeah, you need 3 coefficients, and so the number of rows in the second matrix must be 3. Okay, and here we kept track of 2 linear combinations. So you could keep track of 20 linear combinations, 30 linear combinations, any number you want. Okay, there's no restriction on the number of columns in the second matrix. Yeah.
So for 30, I go to the second number of columns next to the first row.
And if we switch the order, number of columns of the first matrix must be equal to the number of rows of the second matrix.
So if we switch the order, then
no. In this case, it will still work because they happen to be just the right size. But no. So matrix multiplication is not commutative. But it's perfectly possible that you could do A times B, but not B times A. Okay, that's completely possible, right? In that second example, okay, the matrix multiplication I've written, it's not possible in the second row. But if you switch the matrices around, you can multiply that. Okay, so matrix multiplication is not commutative. We'll see all of this in the next module. Okay, but right now we just need this intuition. Okay, right now, for now, it's good enough to know this part. Just matrix multiplied by a column vector is a linear combination of the columns of the matrix. Okay, just knowing that for now, that's what we are aiming for. Okay, when you do actual matrix multiplication, all you're doing is keeping track of multiple linear combinations. But we'll come to this in the next module. Okay, for now, we just make sure we understand this. Okay, and sure enough, like for those of you who have done the dot product way, okay, what's the first entry of the linear combination? Alpha 1 times 1 plus alpha 2 times 0 plus alpha 3 times 3, right? And what's the root matrix multiplication you learned? Take for the first entry of the product, for the first row, first column, take the first row of the first matrix, first column of the second matrix, and take the dot product. Okay, so that is alpha 1 times 1 plus 0 times alpha 2 plus 3 times alpha 3. It's exactly what you would get with the first row here. Okay, so it is consistent with what you know. Okay, but this is a lot more conceptual, and this is the way we are thinking about things. Okay, so any questions? Okay, yeah. Yeah. No. So each linear combination, the first column is a linear combination of vectors with two coordinates. So the first column is also a vector with two coordinates. The second column is also a vector with two coordinates. Okay, so two coordinates. So this will be a 2 by 2 matrix. We'll see all that in a lot more detail in the matrix multiplication. Right now, I want you to just be familiar with this. I only mention this because I don't want you to think that this is something different from what you have learned. It's just consistent with what you have learned. This part we will pay a lot more attention to down the line. Okay, good. Okay. Okay. So one last thing, if you wanted to know, okay, so there are three vectors here, 1, -2, 0, 1, and 3, 2. Okay. Suppose I wanted to know if, give me another vector with two coordinates, -1 and 3. Okay. -1 and 3. So if I ask this question, is -1, 3 a linear combination of 1 -2, 0, 1, and 3, 2? Okay, if I want to ask this question, how do I pose this question? So any linear combination of these three vectors, okay, if I write any linear combination of these three vectors, and now I'm just going to write it, I'm skipping a step and just writing the matrix multiplication, right? So but to say it out loud, if I want a linear combination of these three vectors, okay, if there's a linear combination of these three vectors, it will be like number alpha 1 times the first vector plus number alpha 2 times the second vector plus number alpha 3 times the third vector. Okay, that's a linear combination. Okay, but that happens to be this matrix multiplication. Okay, so when I write here, so if I want to ask this question, is -1, 3 a linear combination of these two? What I'm asking is there any alpha 1, alpha 2, and alpha 3 that satisfies this equation. Okay, is there any alpha 1, alpha 2, alpha 3 that satisfies this equation? Okay? And that you call it as solving sets of linear equations. Okay, so when you're solving sets of linear equations, you're just testing if the target is minus 1, 3, if the target is a linear combination of the columns. Okay, that's all you're doing when you solve linear equations. Okay, right, and we'll see a lot of this. We'll see a lot of this down the line. What we will do now is, okay, it went on a little longer, but we still have 10 minutes. Maybe we start working on the first problem in the module. Okay, so let me